Welcome to everyone who's watching this virtual presentation. I'm Bob Stahlbush from the Naval Research Laboratory, and I'm here to give you an overview of the work that we've done for Power America over the past year. We have 3 tests for Year 5. The first 2 have to do with doing UV-PL imaging and interpreting the defects from the pictures. The first one is if we're doing the work ourselves with our UV-PL setup. We're also assisting Power America partners who have their own commercial systems and helping them interpret the results. The final task is looking at a setup which we've created that uses 2-photon absorption to look at the depth profile of lifetime enhancement, and we can look through very thick layers with this. In this presentation, I'm going to focus on 2 aspects of what we're doing because of the limited time. The first is to discuss what difference we see in BPDs and other extended defects as we go to thicker epitaxial layers. The second has to do with the lifetime measurements we're making. In the future, IGBTs are going to replace MOSFETs as the primary device type or device. Anyway, it's going to be a device that requires a long lifetime in the drift layer. And certainly IGBTs will need that for optimum performance. And we'll be reporting on the results of work that we're doing in collaboration to evaluate thick epitaxial layers and look at their lifetime throughout their whole thickness. I'd like to make some general observations of defects in silicon carbide epitaxial layers over the past 5 years of the Power America program. During that time, we've looked at epitaxial layers ranging from 5 to 150 microns. And I would say that the quality over this whole range has improved. For thinner epitaxial layers, say 5 to 30 microns, the BPD concentrations are negligible and device yield is not significantly affected. Once you get to thicker layers, say over 50 microns, there often is a higher concentration of BPDs, and in that case, yield is affected. Now, one thing that's certainly different is that the BPDs that enter the epitaxial layer from the substrate, which in the past was the biggest problem, is no longer a significant problem. And furthermore, most of the BPDs that are in the thick epitaxial layer are introduced during the epitaxial growth. This is the first of 2 mechanisms that I'll discuss for introducing BPDs into epitaxial layers during the growth. It involves downfalls that fall onto the epitaxial layer as it's been grown. In thicker epitaxial layers, because first you have a faster growth rate, and second of all, because you've got a longer growth time, there's more chance to have these downfalls. The downfalls are a combination of misoriented 4H and 3C polytypes, and they introduce a strain field which causes a cluster of BPDs to surround them. Furthermore, if you have any strain in the epitaxial layer, which is almost always, the longer the growth, the more time there is for the BPDs to glide away from the original cluster around the inclusion. And in the bottom drawing on the right, you can see the BPDs that are gliding away from the inclusion. In this particular picture, they glided away more than a centimeter. BPDs can also start at the epitaxial growth surface, presumably due to instabilities at the growth surface, which may be driven by the faster growth rate involved. In this image, you see both cross-sectional views of the schematic of what's happening, as well as UV-PL images below, which show the plane view. In the center of the 3 UV-PL images, you see an arrow pointing to the origin of one of these BPDs. And from that point, it spirals around itself multiple times, and you can see the multiple BPDs which all move to the left, in this case, which means they're moving towards the substrate. And you can see a pileup of the BPDs at the substrate. That's evident in both of the middle and the right pictures. The other thing that's to note is, and this probably shows up best in the left-hand picture, is that they can migrate a long distance away from the original origin, so they affect a large area of the wafer, causing degradation. The final slide about BPDs is from a wafer we examined in the last year. If you look at the full wafer image on the right-hand side, probably the first thing you notice are the bright bands coming down from the top and from the bottom. Those are BPDs extending from the edge, and they extend quite far into the wafer, several centimeters. If you look at area number 1, which is sort of near the edge of one of those bands, you can see you can see the density, and the density just gets higher as you go closer to the edge. You can also see a inclusion with a cluster of BPDs that's labeled area 2. You can see it in the full wafer image, and a blow-up is shown on the right. Now, in the areas where you don't see much on this wafer, it's not saying they're not there, because when you look at a blow-up, such as area 3, you can see there's in area 3 on the right, the image on the right, you can see there's a half-loop array, which is, so you can think of it as another type of BPD. It's extending in that image 10 millimeters. So, and there are other areas within that supposedly clear area that have similar defects. So it has a fair amount, although I will say that compared to epitaxial layers grown by the same vendor 2.5 years ago, it's a big improvement. This slide starts the second topic. It includes a summary of the carrier lifetime properties needed for a 20 kV IGBT. In particular, it probably needs a lifetime greater than 10 microseconds. Compare that to as-grown epitaxial layers, which are about 1 microsecond. And to optimize the IGBT operation, is necessary to control the lifetime from top to bottom of the drift layer. There presently are 2 methods commonly used to enhance the lifetime, either oxidation of about 1400 degrees C, or carbon or nitrogen implantation followed by high temperature anneal. Furthermore, to achieve the top to bottom control, you need lifetime measurements that are non-destructive and the ability to measure at any depth. We have started experiments in collaboration with Wolfspeed. Wolfspeed is providing the epitaxial layer, which is 175 microns thick, and they are also doing the oxidations at 2 temperatures, 1350 and 1450. The plan is to do a series of short oxidations so that we can track the depth profile of the lifetime as the oxidation time increases. The measurements to measure the lifetime will be done at NRL using a 2-photon absorption technique. It's non-destructive, and we can determine the lifetime at any position from the top to the bottom of the epitaxial layer. This is a schematic of our measurement technique. Note that it's non-destructive. A subband gap laser pulse is focused by an objective to a small spot, and only at that focal point are electron hole pairs produced. That spot can be moved up and down to sample any portion of the epitaxial layer. From the decay curve, as you see in the upper right, we can extract the lifetime. Here are the results so far. We've done 3 cycles of oxidation followed by a lifetime measurement. The 3 times were 5 seconds, another 5 seconds, followed by 15 seconds. By comparing the experimental data, which you can see in the upper right, to the calculated curves, we can determine the lifetime at each of the time intervals. Those calculations account for both carrier diffusion and the surface recombination velocity. In the chart, you can see that at 50 microns and at 1450 degrees C oxidation, there is a steady rise of the lifetime. However, if you go to 90 microns, we have not seen any increase yet. And if you look at the 1350 degree data, we also have seen no changes for any of the times. In summary, for epitaxial layers that are in the 5 to 30 micron range, BPDs are no longer a significant problem for yield. However, for the thicker layers, which often have higher concentrations, device yield is still affected. We also observed that BPDs in today's epitaxial layers are primarily introduced during the epitaxial growth. We've also started experiments with Wolf speed to measure the dependence of the carrier lifetime on oxidation temperature, total oxidation time, and depth position within the epitaxial layer. Thank you.